podcast time.
Good morning, everybody. I'm glad to have you here back on our podcast series with Dr. Ram Hashmonai. Good morning, Dr. Ram.
Welcome, Michael. I'm glad to be here.
Thank you. And this day, and actually today, I want to talk about more of the science behind the OGI camera. How does it look like? How does it work? How does it performs? And I know you're the guy to talk about science as our, chief science officer. So please.
Yeah, OGI camera is a thermal camera, and thermal camera usually can measure the field of temperatures in the field of view of the camera. In the case of the optical gas imaging, we are actually measuring the temperature of each pixel of the background scenery. And if nothing changed in that scenery, we don't see it's like a still picture. But if something changed, like gas coming in between the background and the camera, we are able to see it because on the thermal camera there is a special filter that exactly on the spectrum of the gas absorption feature. And if a gas is between the background and the camera, it will reduce the temperature of the background or increase the temperature of the background, depends on the conditions. And the change in the background temperature, that's what we see like gas. We actually don't actually see the gas, we see the change in the background temperature that is caused by the gas.
Okay, so I have this question asked, very much because people who are not from the field, they're not really aware of how this really works. And the normal assumption is that we can just see the gas and project it, right?
So the most important thing here is what we call the temperature difference between the background temperature and the air temperature or the gas temperature. And what important here, if we have a big difference, it doesn't matter if the difference is positive or negative, we will see the gas more sensitively. We'll see the response of the gas or the impact of the gas on the background temperature that I just explained will be greater. So we are trying to optimize or maximize this temperature difference, we call it delta T, between the background temperature and the air temperature. So one more thing to add, if the temperature of the background is colder, like the cold sky, actually the gas is adding more energy. The gas itself, everything in nature emit radiation, thermal radiation, and the gas in its temperature will emit thermal radiation. So if the gas is warmer than the background temperature, it will add energy to the background. But if the background is warmer than the air, the gas will absorb the energy from the background into the camera, and the change will be a reduction of temperature. So we have two scenarios. One that is the background is colder than the air, and one is the background is warmer than the air. But in both of them, what really make a difference is the absolute difference between the background and the air. That's what will determine the capability to detect the gas and to see the gas.
So okay. That's great. Thank you for the explanation. Because normally people who are not aware of the technology, they misunderstand, or maybe somehow they do not really get into the point, because they think it's like the regular camera. When you get the image, you get a straight line of video, but they don't really get in this idea that each and every pixel there is a standalone thermometer. And like when you take in what you're getting from the camera, it's not really a picture. You're getting a list of thermal readings, right? So, and then our algorithms translate it to some kind of image that could be interpreted by somebody.
Yeah, and if we can determine this temperature difference between the background and the air, we can quantify at each pixel what is the concentration along that pixel path. So this is a very powerful because it gives you a lot of concentration points. I used to have to work with open path. We have one path and we measure the CL, which is the product of concentration time the path length. Here we have in QVGA camera, which is 320 by 240, we have 76,800 pixels.
Correct.
So we have 76,800 measurements of temperature.
Right.
And on each temperature measurement, we can make a gas concentration determination. This is the basis for the quantification. It's not just that we can detect, we
Right.
can also quantify in each pixel what is the concentration. And it really depends if we know what the gas that is emitted. If we don't know, the OGI cannot differentiate.
Wow. Well, that's very interesting. But then, and that's actually leads me to this next question, because normally people would accept, the cameras to be 4K, 8K, whatever case they are, in the home edition cameras, and then when we come and start, talking about the resolution, they say, "Oh, this is like very poor resolution to those camera." But is there any reason behind that? There is this lower rate of resolution?
Yeah, the lower resolution, we have a bigger pitch on each pixel, which is the size of the pixel.
Correct.
The pixel is more sensitive for the energy, so we can be more sensitive in each pixel. So for sensitivity perspective, we prefer the low resolution. The image is less clear, less sharp, but for gas detection and for gas quantification, we actually do the opposite. We actually take this and we are trying to bin to get more sensitivity. We are cluster together group of pixels, like 3 by 3 pixels, 5 by 5 pixels, and get the information on concentration on a group of pixels. That's why we get more sensitive. We actually reduce the resolution for gas detection and not increase the resolution. But typically people would like to see reasonable. So between 640 to 320, it's a 4 time, because it's a,
you have to
it's a
divide the
square.
pixel to 4 parts.
Yeah, a frame is a square. So the resolution between 320 to 640, we have four times the number of pixels in the image. You get clearer image, everything is sharper, you can focus it very nicely, but you pay with sensitivity. But nowadays we can find by doing some tricks with algorithmic and binning, what I described, we can retain or regain the sensitivity that we need for quantification and detection. And we don't need to worry about going to higher resolution, but we should not exaggerate, because sometimes you go to higher resolution, you decrease the pitch. Now we're going to higher resolution in our next generation of cameras will go to 640. Our current camera is 320, but we go to 640 and we decrease somewhat the pitch, but we don't exaggerate. Because if you decrease the pitch too much, you pay too much in sensitivity, you cannot afford. What you gain is the detector is lighter and even sometimes cheaper.
Right. So on my end, taking that to consideration, my end is like, when I'm going to a facility to do an inspection, I would expect the equipment to be, on the highest level of sensitivity. However, I don't want to discriminate, or I don't want to give up on that good picture scene. So is there any kind of solution in between, like keeping the pixel running at the same size and getting more of a picture?
I started to say we have algorithmic improvement that we could do some, as I mentioned, binning, some averaging, some tricks that will make the plume of gases look better, even in low resolution. So, but I think the demand for higher resolution is coming from the clients because they don't consider and do not understand fully the importance of sensitivity.
Right.
So they are willing to pay the price, but we hold it very tight, not to compromise too much on sensitivity. So we will not go, in my opinion, more than 640, because what you need is to see in the relevant ranges. What you need to see is where it's coming from. You don't need to see, features that have high resolution. You don't need it for gas detection, but people still like the higher resolution. Higher resolution is better.
Of course, obviously, especially today when you have the phones that can produce like brilliant images, and eventually looking at those images, you would like to have a camera that paying some money for, and you would expect it also to be some high res thing. But
Usually the resolution is a problem when you change the focal length of your lens and you increase it, then it's become very pixelated with the low resolution. Where you're looking at long range with a magnifier,
right.
so you can see.
So, and back into the one of the first questions, I'm just having this idea of explaining really what the camera sees, and somehow to get, when you have the blockage or emission of energy from those gas molecules, because basically it's not like a stick object there, right? It's molecules of the gas that
So
are
we're measuring
creating.
the change.
Right.
It's not a stick object. It's in and out. Each frame, the value of the blockage or the emission
Correct.
is changing. So if we don't see any change, it's not, there is no gas. But once we see a change, we have ways to know if it's a gas or because we see the change by dust or steam plumes, but they are behave differently in the atmosphere. So we have ways also automatically discriminate between the scenarios.
Hold on. So it will be both, or it is both on the handheld devices and in the fixed devices, or is solely for the fixed application?
In right now, you don't need it. You don't need it in the portable, because you have your eyes and you can
Right.
see if you have steam or not. But it's mainly developed for the fixed, to have reliable alerts and detection, automated detection for the fixed camera. But in the future, once we have a image stabilizer, we can apply this way also for
For the handheld.
yeah.
Right. So, and going again back to the science. So for me, as we said, we have this changes of energies that the gas molecules are creating, or the differences that they are creating. How do we take this huge amount of numbers and digits and this huge Excel spreadsheet with all of that stuff, and kind of creating, as we said, for the quantification, the mass flow, because that doesn't look it looks very complicated. How do you take it from one pixel to a flow, and how do you
Yeah,
how is it created?
there are different. First of all, you need to accurately calculate the concentration in each pixel, concentration length. Once you achieve that, one of the conditions is that you have enough delta T at that pixel. You need to have you need to know which gas it is in order to get the concentration right, because each gas have different interaction with the delta T, and the response is different for each gas. Some gases are more sensitive, some gases are less. So once we have this, the basic unit pixel quantification at the level of concentration, you want to convert it to mass flow. And so you take the mass concentration and you integrate it on a cross section downwind from the source.
Okay.
You integrate the whole mass in that, and you need to know what is the rate of the flow that crossing this cross section. If you know the wind speed and you know the integration of all concentration in the plane downwind, you have everything you need to calculate the mass flow. So what we are working now is to develop a way to take or to accurately measure the wind speed from the images, the changes in the images, and have this very accurate, the temperature difference very accurate, the temperature of the air very accurate, and then we'll get the concentration, mass flow, everything very.
Yeah,
We
well,
get closure on the problem that we have.
so you're taking us to the very next stage of the quantification with the OGI. But there is some, basic things that are still, some people are asking or and having questions on. So we have the mass moving from one place to another, right? We
Yeah.
have the period of time, we have the wind speed, we have all of the data, right? So in that case, how do you do it for like an automated system? And I guess this could be a challenging one, right? When you have a lot of things moving around the site, or you're looking in a very big area, because today the quantification is solely for closed objects, right? Like within the closed premises. Like how do you do the quantification on the long range when you have 70 meters, 120 meters? How do you quantify that?
For me, on the fixed, and actually, when we ask people to quantify, we ask them to put it on a tripod. Otherwise, they cannot do it. So the fix is good for us. If we have the camera moving while we do the quantification, we cannot we cannot calculate what is the change caused on the background energy by the gas. We can have the temperature change because we move the background pixel by moving the camera. So we actually prefer the fixed. About the long range, it's a matter of sensitivity. So I mentioned we have ways to know if it's a gas. And once we know what type of gas it is, and we are above our detection limits, and we know we have enough delta T to calculate the base concentration, range is not a factor. So range is what I described before. It's the same process. You just
How do you compensate the difference? Because once you increase the difference, you obviously increase the amount of energy that could absorb, because it getting distracted by
it's
the
all
atmosphere.
relative to the background. It's all normalized to the background temperatures that also come from a distance. So you have to take with distance some consideration of atmosphere. We do some correction for that, but generally they are negligible compared to the basic determination of the background temperature, the air temperature, and the wind speed. And you need to know what gas it is. If you have all of this, you could have accurate quantification.
Okay, great. Thank you, Dr. Ram. So, just summarizing that's I think will be several parts of this discussion, because I do think that we have to get more into the details of really the numbers and maybe the formulas and so on. But for today, I guess that will be enough. Thank you very much.
Thank you, Michael.
Thank you.
Bye.